Okay, so it is 11 o'clock and hello and welcome to the ASCE IGS webinar series today on Tuesday, the 18th of January 2022. My name is Ryan Hackney and I am the Secretary of the ASCE IGS and I will be hosting today's webinar. ASCE IGS is the Australasian chapter of the International Geosynthetics Society and it has been established for 20 years. We are one of the 45 chapters globally, which combined have over 4,000 individual members, over 500 students, and that includes over 190 corporate members. The Australasian chapter covers the interests of Australia, New Zealand, and the Pacific Islands. By becoming a member of ASCE IGS, you also become a member of the IGS, and there are many resources available directly on the IGS website. This includes educational documents, lecture series videos, a library of IGS proceedings, and also free access to technical journals, including Geotextiles and Geomembranes and Geosynthetics International. You can access the website at geosyntheticsociety.org, or you can use the QR codes that you see at the bottom right hand side of the screen. ASCE IGS, we also have a website that you can see on the screen right now, and again we have many of our own resources available. This includes a dedicated student section. We have current news that's updated weekly. We have upcoming events that we're hosting. And there's also information on how to become either an individual or a company member with ASCE IGS. Our resources include the webinars that we've recorded today, plus the other events that we have recorded. This includes the seminar series and our popular panel forum debates that we introduced last year in 2021. If you've missed any of our webinars, be sure to go to the website to check these out. If you would like a certificate of attendance for today's webinar, please just email us on info@aceigs.org with your details and we will organise an attendance certificate to be sent back. Here is a quick reminder of our upcoming Geosynthetics Conference, GeoANZ. This will be held in Brisbane between 7th and 9th of June this year. The early bird registrations are open and the abstract deadline is approaching in 10 days now. So that will be the 28th of January. So be sure to start submitting abstracts if you haven't already. And a big thank you to Geofabrics Australasia, who have sponsored today's webinar. We will hear a case study from their applications engineer, Dr. Abid Ali, after today's main presentation. And moving on to today's webinar, we have a very special guest, Professor Jie Han from the University of Kansas. He will be educating us on designing with geosynthetics for unpaved roads. And to give a brief introduction, Dr. Jie Han is the Glenn L. Parker Professor of Geotechnical Engineering in the Civil, Environmental and Architectural Engineering Department at the University of Kansas. He received his Ph.D. degree in Civil Engineering from the Georgia Institute of Technology in 1997. He has gained extensive teaching, research and industry experiences in geosynthetics, ground improvement, pile foundations, bridge structures and roadways. Professor Han is the sole author of the book entitled Principles and Practice of Ground Improvement, and he has published approximately 450 peer-reviewed journal and conference papers. Professor Han is a board governor of the ASCE Geo-Institute, a council member of the IGS, a past chair of the ASCE Geo-Institute Soil Improvement Committee, and the chair of the TRB Transportation Earthworks Committee. Professor Han has been invited to give more than over 200 keynote and invited lectures and short courses around the world, including the State of the Practice Lecture at the 21st Annual George F. Sowers Symposium in Atlanta, Georgia, 2018, the 18th UK IGS Lecture in London in 2018, and the 3rd Robert M. Koerner Award Lecture in 2021. He's received numerous awards from the profession, including, but not limited to, the 2021 Shamsher Prakash Prize for Excellence in Practice of Geotechnical Engineering, the 2014 IGS Award, the 2017 ASCE Martin S Kapp Foundation Engineering Award, and the 2018 ASCE Kansas City Section Engineer of the Year Award. Professor Han was elected to the ASCE Fellow in 2014. So, if there are any questions during today's presentation, please post them in the Q&A section at the bottom, and be sure to include your name so we can get any questions that are unanswered back to you. So that is the end of my introduction, and I will now hand over to Professor Jie Han. Thank you.
Okay, thank you, Ryan, for your kind introduction. First, I'd like to congratulate your chapter for the wonderful webinar organized in the past couple of years. Those are really great lectures to educate the public about geosynthetics. It is my great honor to share with you today regarding the designing with geosynthetics for unpaved road. So in this presentation, I will start with the introduction, and I will talk about the mechanism, design concept for use of geosynthetic to stabilize unpaved roads. Then I'll focus on the design with geosynthetic for stabilization of unpaved roads. At the end, I'll give a few concluding remarks. So I'd like to start with the real story with this situation. And walking on the soft soil. You may have some problem with my accent with L and R, but this is a true story I want to share with you. It's an interesting story. Several years ago, I got the research project from Kansas Department of Transportation to evaluate the box cover and the traffic loading. So I asked one of my students basically go inside the box cover. The picture you look at here now is inside the box cover. During the years, because there's a lot of soft soil deposit at the bottom of the box cover. Those soil really is got clay material, very sticky. And when my student went inside, basically he stuck in the soft soil and could not get out from the box cover. We handed the ladder to him and asked him to pull him out. Of course, for this kind of situation, it is impossible for him to walking inside the box cover. Then we have to find a way to stabilize this soft soil, even though the thickness is not very large. It's about 30 centimeters. But this picture basically shows the different techniques that we use, try to stabilize the soft soil for him to walk inside the box cover. The first thing we tried, as you can see here, basically we collect some tree branches, try to put on top of the soft soil. As we know, beaver use tree branches to build a dam. And this is great material to reinforce. And when we collect the material, because the material is not enough, and when he work on the tree branch, basically slipped off. Then he came out with another idea, tried to buy some plywood and from the local store and put down on the soil. At the beginning worked pretty well, but when the plywood getting wet, get muddy, and also he couldn't basically work on the slip away from the plywood, just like unbalanced beam situation. And then he said, well, I learned some geosynthetics from you. How about let's try geotextile? And then we placed the geotextile on top of the soft soil, and then he worked on it and still sinking in, as you see here, those the footprint of him. Then we tried the last one, basically Geogrid. And we placed Geogrid, that's what he's standing on, and they working on the soft soil. Now, what's the difference between Geogrid and the geotextile? Geogrid, as you know, had the bending stiffness. Even though the bending stiffness is not very high, but that's enough to support the person working on the soft soil. Now, suppose all material can work to reinforce soil, just because of the condition. For this case, Geogrid performs the best, but does not mean geotextile cannot be used to stabilize soil for roadway applications. Okay, so we need to understand the limitation. We need to understand what we need to stabilize soil like this. But this story I share with you basically is try the error approach with basic knowledge of improvement or stabilization. Is this a really state of practice? So let's take a look at the state of practice for pavement design in the United States. So what I cover today may be different from what you are doing in Australia or other countries. But as we know, in the past 40-some years, we have been used the ASCE 1993 design guideline was developed based on the statistic approach. So this is empirical method. Then after that, the federal highway, the ASCE had been pushed for new design method called mechanistic empirical design method. So this is called ME pavement design, also called MEPDG. Now, what is the state of practice? Basically, kind of in the between from the transition from empirical to mechanistic empirical design method. Today, what I will share with you regarding the design with geosynthetics for unpaved road based on the state of practice. Basically, I will talk about some empirical design method, and also we'll talk about mechanistic empirical design method. But today, I will focus on unpaved roads. As you know, geosynthetics can use for many different applications, including paved roads. The unpaved roads I want to cover today, there's two different situations. One dealing with the local gravel roads. For this case, and for the remote area, because the lower traffic volume, and we do not need the expensive asphalt pavement, the concrete pavement, often we use gravel road. For gravel road, we also can allow a little bit deformation, as you can see the writing here, but you don't want to have a very large deformation because that will not be good for vehicles. Now, another situation dealing with for temporary or hollows. For this case, basically the road only used for construction purpose, for truck to carry material in and out. For that situation, you may allow the large deformation. Now, for some situation, you may want to limit deformation for the side. I will share with you two different applications. Before I get into design method, I want to talk about one important parameter often used to design roads. So that parameter called California bearing ratio, or CBR. So this is the setup for CBR test. Basically, you're all familiar with compaction mode. So you compact soil in the mold, and then you place the weight on top, and then you have a pistol. So use the load to push the pistol into the soil. So it depends how much load you use to push the pistol to certain displacement, and then use the load to calculate by the ratio of the load required to push divided by the standard load to push crushed stone. If the load push the soil is less than the crushed stone, then basically the CBR value will be less than 100%. So the lower CBR means the soft soil. So this is the very nice design chart used by Illinois DOT, try to decide whether we need to use a limited procedure or not, depend on the subgrade CBR. So if the subgrade CBR is less than 6, the guidelines say you need to use a remedial procedure to treat the subgrade. Now, if the CBR is greater than 8 or 8%, the remediation procedure not needed. If between, that's optional. So this slide also gives you some typical design thickness required above the subgrade. And the US Geosynthetic Material Association developed a white paper. In the white paper, they provide a guideline for use of different kinds of geosynthetic with different subgrade CBR values. Now, for most cases, we focus on the soaked CBR because for roadway, the outside, the outdoor, often subject to rainfall, will get wet, get soaked. If we have the soak subgrade CBR greater than 3, for that case, we can use non-woven geotextile as separate. Now, if CBR is from 1 to 3, then you may need to use Geogrid or woven geotextile for the reinforcement. Now, if the subgrade CBR is less than 1, then you need to use Geogrid with non-woven geotextile or woven geotextile. Now, for Geogrid, I will show you in the next slide, basically has opening. If the soil is too soft, under load, the soil may squeezing through the aperture. This is why non-woven geotextile is necessary for very soft soil. So here basically show you different type of geosynthetic used for roadway applications. So we start with non-woven geotextile. This is a woven geotextile. And this is a relatively new product called weakening geotextile. The white fiber basically is the weakening fibers. The weakening fiber can absorb the water or suck the water from soil, then take out to evaporate. So this product has been used to reduce the moisture content in the base course. Because of the time, I will not have time to talk about this product. If you're interested in this product application, I can give another talk in the future. And we have done quite a lot of research with weakening geotextile. The next one is dealing with geonet or geocomposite, mostly used for drainage purpose. But here lists 3 different Geogrid products. The first one is biaxial Geogrid. The aperture size is square or rectangular. But this is a triangular Geogrid with triangular aperture size. But this is a relatively new product just launched last year. It's called multi-axial Geogrid. But for this Geogrid, as you may notice, there are 3 different kind of aperture. But this is one, this is another one, there's another triangular, but with different size. But suppose this Geogrid can provide a better interlock with different size of aggregate. So all those products basically is called primarily geosynthetics. The last product is geocell. This geocell with height, basically 3-dimensional honeycomb shape of geosynthetic products. All the material, if infill in the pocket, will be confined. So let's talk about 2 different applications. One is this one-stage application, as you can see here in the on the construction side with Geogrid, geotextile. Sometimes we have the geotextile at the bottom, and in the middle is Geogrid. This is geocell. But this is the one case I will talk about today. Basically, if you have soft subgrade and you place the geotextile or Geogrid at the bottom here and with base course, or you can use geocell. Now, if the base course is too thick, you may place another layer of geosynthetic to support the load. But this is basically a one-stage unpaved road. So let me talk about the second situation. So this is the same as the first stage. Basically, during the construction, you need to support the vehicle, okay? A construction vehicle. Then after that, sometimes we turn this pavement into asphalt pavement, turn this one to the concrete pavement, then support more traffic loading on the top. So for this situation, I call 2-stage situation. Basically, you eventually will use paved load. For that situation, you don't want to have unpaved load subject too much deformation like rutting. But now we're dealing with 2 different situations. On the left side, basically this is the final unpaved load that can subject larger deformation. For the second situation on the right, unpaved load that use temporary for construction purpose, suppose allow the lower deformation. The one-stage application may allow large or small deformation, while 2-stage application only allow the small deformation on unpaved roads. But in my presentation today, I will cover 2 different situations. One, basically dealing with unpaved road with large deformation. Another situation dealing with unpaved road with small deformation. Okay. But as you may all know about the primary function of geosynthetic as separation, reinforcement, filtration, drainage, containment, the barrier, erosion protection. Now, in recent years, we add another function called mechanical stabilization, mostly referred to ladder restraint and confinement. So I'd like to spend a little bit of time to explain this function. But mechanical stabilization, this is my definition. Mechanical stabilization involves inclusion of non-chemical material like aggregate fibers, geosynthetic into soil to improve the mechanical property, mainly strength and modulus of soil through the particle inclusion interaction. There are here basically 4 examples. That you can mix the fine material with coarse material that create the interaction between large particle and the small particle to improve the property. You can also include the fibers in the soil to improve the soil property, or you can use Geogrid with aggregate interlocking to improve property, or you can place the fill material in the geocell. So all this, the key is the interaction. Okay? Now let's talk about ladder restraint. So basically, in the pavement application, as we know, the base course and the subgrade, we place the geosynthetic at the interface. Under the wear load, basically generate the particle lateral spreading or lateral movement. Due to the shear stress, basically induce the tension in the geosynthetic within certain range. And then beyond this range, actually you will create the compression after that, okay? So this is basically interaction between the aggregate and the geosynthetics. Now there was some numeric study done to analyze the load effect on the pavement base course. As you can see, there's 2 different kind of geogrid. One's a biaxial geogrid, one's a triaxial geogrid. And for this geogrid, as you can see, there's a red zone here. Red zone means tension. And then the blue zone basically is the compression, okay? So as we know, geosynthetic suppose is not used for compression. But in other words, if we cut the geosynthetic here, that will not affect the performance of the geosynthetic because we don't expect geosynthetic to carry any compression, okay? The same thing here, as you see, the outside really will not contribute the load bearing support. Now, another thing, you see that the distribution of the tension in the middle will be high tension and the outside will be lower tension. For triaxial geogrid, create a more uniform distribution of tension, basically generate lower maximum tension than the biaxial geogrid. If you recognize this product SS20, this product has tensile strength 20 kilonewton per meter. But in other words, for this geogrid, only modify 2.5% strength. And for this geogrid, only mobilize 1.5%. So in other words, the tensile strength for this application is not important. The effectiveness of ladder restraint depends on the soil geosynthetic interaction, in which geosynthetic friction with soil and the stiffness are more important than its strength. Now let's compare the 2 different situations in terms of tension in geosynthetic. So this is the one we just talked about. The ladder restraint we refer to mechanical stabilization. Basically, due to the shear stress, the tension will develop within certain range. And the outside, there will be compression. So for this case, typically happens for small deformation. Another situation, what we call like tension membrane. Basically, under load, the tension will develop in the geosynthetic. The larger tension will be developed at the edge of the geosynthetic. In addition to that, there's tension extend into the geosynthetic. Now, for this case, if you think about this, if you cut the geosynthetic at this area, the geosynthetic will not mobilize tension because that maximum tension relies on the anchorage. In addition, the tension membrane will become important only if the deformation becomes very large. For this case, you can see the maximum tension for tension membrane is much greater than the tension induced by the ladder restraint. However, they can transit from small deformation to larger deformation from the ladder restraint to the tension membrane. Okay, the tension membrane requires anchorage. The case what I mentioned at the very beginning, why the geotextile did not work to support that person, because there was no anchorage on top of that geotextile. Okay. Now let me try to summarize the mechanism and the benefit of geosynthetic for roadway application. First, separation. If you place the geosynthetic here, basically separate subgrade and the base course, prevent the intermix or no intermix. Okay. Now we also can use the geosynthetic here to stop the capillary rising from subgrade if the groundwater table is closed. So you can use different kind of geosynthetic to do that. Weakened geotextile have been proven very effective to stop the capillary rising, because weakened geotextile can create a suction to pull the moisture downwards rather than upwards. So for those two situations, basically you can maintain the strength of modulus of the base course. Basically, you keep those material unchanged. Now, next category basically is tension membrane and the vertical restraint. For tension membrane, we already talked about the vertical component of the tension membrane can carry the load. Basically, can increase the capacity of subgrade. Now, for this vertical restraint, basically, if you place geosynthetic here, you can prevent the failure surface go deep. Okay, that will increase the bearing capacity of base course. In addition, for the subgrade and the traffic loading will start to heave, the geosynthetic will try to minimize the heave, will increase the bearing capacity of subgrade. So for this case, basically geosynthetic can increase strength of subgrade and the base course. The last category is lateral. So for this case, as we talk about this lateral restraint through the friction or through the interlocking between the base course and geosynthetic. The place geosynthetic also we can basically take the water out as a drainage. So for that case, we can increase the strength and the modulus of the base course. Okay. Now, in real application, you may have a situation with for geosynthetic used for different functions. You may use it as a separation, you may use it as a filtration, you may use it as drainage, you may use it as a mechanical stabilization. So for this case, as you can see, this wetland, they place the geotextile first, and to provide the separation, this is the granular material, and this also the geotextile here. Actually, this is a composite material as what you see here, that uses Geogrid to provide the mechanical stabilization, use geotextile to provide the function as the separation. The geosynthetic may serve a different function in the roadway application. The generic term improvement may be used for combined functions. Now, geosynthetic can function and provide benefits only the material survived construction and the surface. As you can see from this picture, if you dump a very large sharp stone on top of the geotextile, may break the geotextile, that may make the geotextile lose some of the functions. To minimize this problem, and there's some recommendation, and that depend on the condition of the subgrade, depend on the size of the material you place on, and also depend on ground pressure of the construction equipment. The federal highway provide this guideline, this table, basically depend on the subgrade CBR value and also the cover thickness. So here basically is the construction equipment contact pressure. So as you can see, if the CBR is less than 1%, this guideline suggests you need at least 300 millimeter material cover for the lower pressure equipment. For high pressure equipment, you need to use 450 millimeter material in order to do that. Now, if the subgrade getting stronger, you can use the thickness section as thin as 100 millimeter. And there's two different products they suggest, basically geosynthetic class 1, geosynthetic class 2. The class 1 is stronger than class 2. So as you can see, if you have a stronger subgrade, then you can use a weak geosynthetic for this purpose. Now, for Geogrid, we also have a class 1, class 2, class 3. In addition to the strength, there's two more requirements. One is aperture size. But in order for Geogrid interact better with aggregate, we need to find the aperture size fit with this range. Basically, the aperture size should be greater than mean particle size less than 2 times 85% passing size. There's another requirement. This is basically for interaction purpose. Another requirement for separation. The basically say, as I mentioned earlier on, because Geogrid has apertures, for very soft soil, the soil may squeezing through the Geogrid aperture. For that case, you need to rely on the aggregate serve as a separation or filtration requirement. That for this case, the aggregate D85 should be less than 5 times D85 of subgrade. Otherwise, you need to use geotextile as separator with the Geogrid. Okay? So this is basically to fulfill the filtration requirement. Now let's talk about the typical design concept. That I try to use 2 different cases, one with unpaved road, one with paved road. But let's assume we have a tight contact pressure, 600 kilopascal. But this is the base course material. And through the base course material, as we know from the Boussinesq solution, the pressure will decrease from surface to the depth. But at this point, the pressure may be 100 to 100 kilopascal. But that still is too high, then the soft subgrade may cause the failure, basically rutting for the pavement, but it's a bearing failure. Now for paved road, because we have used the pavement surface with base course, subbase, and the pressure reduction is faster than unpaved road. But the stress at the interface between the subgrade and the subbase may be only about like 10 to 20 kilopascal. So for most cases, the soil subgrade can support that pressure. That will not be bearing capacity failure. Instead, basically, we're dealing with 2 different situations, because if we use asphalt surface, will attract the tensile strength at the bottom of the asphalt that will create a crack at this location that generally called fatigue cracking. Another situation, each layer will contribute the deformation. The deformation will depend on the parameter, basically the zero modulus. Now, for unpaved road, the important parameter will be undulate shear stress. The undulate shear stress, basically, we run the test in the lab. Now, for base course, this is basically the strength-based design approach. For paved road, we rely on the zero modulus. How do we determine the zero modulus? So basically, the cyclic triaxial test. There's a cyclic load, divisional stress sigma d, divided by the permanent. No, this is should be resilient deformation, not the permanent deformation. This is a typo, and we calculate the zero modulus. Okay, so this is basically deformation-based design approach. But even for unpaved road, if we're dealing with smaller deformation, also we need to use called deformation-based design method. But here, basically, show you 2 different situations. This is a rut depth. That's what we focus on for the unpaved road. There's no fatigue failure for unpaved road because there's no surface layer. This is the case, basically, if you increase the number of passes, at a certain point, you have a bearing failure. You may have unstable base or unstable subgrade. Now, for this case, basically, the deformation will increase at a slow rate and getting slower and slower. But this is more dealing with the resilient behavior, and you have a stable base, a stable subgrade. But in my presentation, I was dealing with both situations. Okay. The first one based on stress-based design, the second one based on deformation-based design. Okay. The unpaved road allows the large rod are designed based on strength, while unpaved allows small rod, like a local gravel road similar to paved road, are designed based on deformation. But let me give you a little bit idea about the mechanistic empirical pavement design method developed by Ashton. In this design method, we have a pavement structure. We have a pavement layers, like a surface layer, asphalt, the base course. But we need to evaluate the material properties, and that material property may depend on the climate, like temperature, moisture, and also we need to input the traffic loading here. But after we apply the load, we can calculate the stress of the strength in each layer. That calculation basically calculates the pavement response. This is the theoretical or mechanistic method. Now, but really what we care about the distress. This shows the cracking, rutting. How do we transfer the stress strength to real deformation through one empirical relationship called damage accumulation curve. So for this one, basically is mechanistic. So this is empirical. If you tie them together, becomes a mechanistic empirical pavement design. Now let's talk about the response model. This is the layer elastic theory proposed by Burmester back in 1945. We have the pavement layers and we have subgrade. This is high pressure. If we apply the pressure on top of this, if you use a Boussinesq solution, what we learned from soil mechanics, you will get this kind of distribution. Basically, the stress at the center will be higher than the edge. There's a distribution. But in the practice, we often use called distribution method to simply calculate or estimate the stress under the footing or under traffic loading. So that is a stress distribution that will involve the distribution angle. Now, if we're dealing with the pavement, then we have a stiff layer over subgrade. For that case, basically general situation, the modulus of E1 is greater than modulus of E2. But for this case, basically Burmester developed a solution for that to calculate the two-layer system. So for this case, if you increase the modulus for pavement, you can reduce the stress at the interface, okay? So from red line to blue line. But if we use a simplified method, then basically we will get enlarged distribution angle and to calculate the stress at this location. But the benefit of with stiff layer, basically distribute the load to the wider area to reduce the stress at the interface or on top of subgrade. Okay. Now we did some study to measure the stress under the loading plate. For this case, like 550 kilopascal, and we have asphalt layers, base course, subgrade. Now, based on the Burmester solution, we can take a look at what kind of reduction you may have. Let's start with the Boussinesq solution. The modulus E1 equal to E2. You have like about 65% the stress will transfer at this location. Now, if we increase the modulus by 5 times, and then you reduce the stress from 65% to 40%. Okay, that is a reduction. We did observe that phenomenon in our test. We use a control section, and with the geocell section, the red one basically measure in the control section, and the blue one we measure in the geocell sections. But indeed, there's a reduction. But geosynthetic help reduce interface vertical stress. Okay. Now let's talk about the design with geosynthetic for stabilize of unpaved road. There are many different design methods available, and I will pick up some design methods, share with you. The first method is Stewart et al. 1977. Then I will share with you the method Dr. Giroud and I developed in 2004. And those are the strength-based design method. And then I also will talk with you a little bit about the method developed by 2 of my PhD students, Yang and Sun, in 2013 and 2017, based on the deformation design. Okay, the Stewart et al. Method, basically based on the Boussinesq solution, uniform media, to calculate stress at the interface between base course and subgrade, and then check the vertical stress less than the bearing capacity NC times C. Okay, but in this method, they divide into 2 different situations: without geotextile, with geotextile, and also dealing with 2 different rod depth, with small rod depth, with larger rod depth, and it came out with different bearing capacity factors. But in general, without geosynthetic bearing capacity is lower, with geosynthetic bearing capacity high. Now in US, typically we design for 75 millimeter rod depth. Now for this case, basically the bearing capacity for without geotextile is 3, with geotextile 5.5. Okay, but as you can see, with the higher rod depth, basically bearing capacity will be high. That indicate that at the high deformation, the bearing capacity will be mobilized more. But when I talk about the method Dr. Giroud and I developed, we also adopt this concept. But they developed a design chart, and I'll go through one simple example here. if we have a single wheel load, load 45 kilonewton, 2,000 passes, subgrade CBR 1%, and we can estimate that the undressed strength is 30 kilopascal. And without the geotextile, use the bed capacity factor 3, we can calculate CNC is 90 kilopascal. With geotextile, use the bed capacity factor 5.5, and calculate the bed capacity factor times C is 165. But if we go to the design chart with single wheel load, and if we know the CNC is 90 for this case, and go to find the single wheel load, 45 kilonewton, and we go there, can figure out what would be required thickness for without geotextile 475. Now, if we increase CNC to 165, use the same chart, go there, we can figure out with geotextile, now the required thickness is 325. But if you calculate the difference, basically 32% the base thickness reduction for this case, okay? Okay, now let's move on, talk about the method developed by Dr. Giroud and then myself, published 2 papers in 2004. This paper has been included in the Federal Highway Design Manual for Geosynthetics. But in this design method, first we check the required base thickness for traffic loading. Now for this case, we need to make sure the base course is strong enough to support the wheel. So for this case, if we know the tire pressure here, I apologize for the English units here, but just for illustration, if you know the wheel load and they go there and they find out what the base CBR value, and you can figure out the number of passes this base course can carry. The actually base should be strong enough to support traffic. All design methods assume base is strong enough. But if your base is not strong enough to carry the traffic, it doesn't matter how you treat the subgrade. But that is important concept. Now let's assume the base is not strong enough. That we use the stress distribution method to calculate stress on top of subgrade. But this is the method we talk about, use the stress distribution method. But we convert the Burmese solution with the layer elastic theory. Basically, those are the dots for the Burmese solution into the simplified solution with the distribution angle. But let's see if elastic modulus ratio E1 equal to E2, if the ratio equal to 1, they will go back to uniform distribution angle, just like a Boussinesq solution. If you increase the modulus ratio, you will increase the distribution angle. Now, how do we measure the distribution angle? You can place your cell here. Based on the measures of vertical stress, you can calculate what will be the distribution angle. But this is based on the static loading. But in real application, we know dealing with traffic is dynamic loading. But actually, this is a simple method for a response model. Now, in the traffic loading, we know the traffic is changing with the passes. But for this case, as you can see, there's the initial distribution angle, and the distribution angle will reduce with the time because of the deterioration of the base force until to a certain point, the balance capacity fails. But we got some test results with the control section, 2 different geogrid. We observed the distribution angle change with the number of cycles. But we proposed the formula. This is empirical formula. Basically, the distribution angle changes with number of the passes and with the lambda. The lambda is distribution angle reduction rate, depend on the geosynthetic products and base thickness. But in other words, if you have a stiff geosynthetic, you will reduce the deterioration of the base course. Now, alpha 1 basically is the static loading, okay, distribution angles. The empirical formula considers the base damage with traffic. But based on the concept we talked about earlier on, we calculate stress at the interface, and then that stress should be less than the balance capacity. Now, the balance capacity factor here, we apply the one called balance capacity mobilization factor at a different rod depth. As I mentioned earlier on, for Stowe method, they're dealing with 2-inch, 4-inch, but if you include the M factor, you can consider the rod depth at a different the m value is different depth. If you solve this equation, you can calculate the required thickness. For different products, you have a different bedding capacity factors. For control is 3.14, geotextile 5.14, geocell 5.14, for Geogrid 5.71, because Geogrid provides rough interaction with that. But we calibrate this formula to get this equation that involved one parameter called J, basically actual stability module for Geogrid. But there's an ASTM standard to determine this J. The J basically is the torsion rigidity of the nodes of Geogrid. Okay, but in this one, basically this is the K prime value depend on the geosynthetic products. If you have your product, you can calibrate this term for your product. But we developed the design chart as well for specific products. If we now in this formula, we need to use iteration to solve the H. Actually, you need like a 2 iteration to solve that H value. But if we have CBR1, you can go there to determine is 0.3 meter for the Geogrid sections. Okay, but that was study done by my former PhD, Dr. Prakash. He calibrated this method with geocell, because for geocell there's a new J factor. But this is a term basically was calibrated through the test results. Now let me move on to talk about the mechanics empirical design method. Consider compaction-induced residual stress. But this is the case dealing with the geocell. But initially the stress at this A level, basically, and then if you have a roller, and basically the stress will increase through the K knot line. If the roller move away, this will generate the unloading. And because this is a failure envelope, if you don't have a geocell, the stress will reduce to here. They will generate the residual stress for control section. But if we place a geocell, prevent the passive failure, we cross to here, then we generate the stress, increase the residual stress for geocell. Okay, so that is the benefit. But in this model, we use the residual modulus through the residual modulus test to determine those constants. And then we use the test section, moving wheel test. We have 4 sections, 2 non-stabilized without geosynthetic, 2 sections with geocell with different thickness. Here just show the test equipment. This shows the geocell. Here basically 2 non-stabilized sections, those 2 geocell sections with different thickness. But we use the numerical model called Flex 3D to do the analysis to determine the stress strength in the base course and the subgrade. And here basically say before the compaction, this is the overrun stress. But this is the control section without the geocell. This is the difference basically residual stress induced by compaction. But this is the one basically induced by geocell for different sections. Okay? So based on that residual stress with the load, we can calculate vertical stress for each section, the 4 sections here. But eventually we use this empirical model. I will not get in detail. Basically, this is the permanent deformation strength. The most important thing is the elastic strength calculated from Burmester solution. But from that, we can calculate rod depth for each layer you add together. But we determine those parameters based on the test results. But eventually, we show the comparison for the section. The section 1, the dotted line is the test results, the red line basically the predicted results. Section 2, they match pretty well. Unfortunately, section 3 did not match very well, but I will explain to you why. Section 4 matched reasonably well. For ME method, as you can see, we can predict the deformation. But for the stress design method, you will not really show that much. Okay. The reason for the difference for the section good match, the geocell actually maintain good shape. But for the section with poor comparison, section 3, because the geocell collapsed. Okay. important things is the mechanistic imperial design method is applicable to the condition where base and the subgrade are stable. If there's any failure, this method will not be able to use. Okay. Now, this method involved the numerical analysis. Sometimes people say, well, that's too complicated. But we propose another method, basically, is alternative method, use the current mechanistic imperial design method, basically to come out for equivalent modulus. But for this case, we have a geosynthetic here. That you can equivalent based on different criteria, based on the equal stress at the interface, or based on the equal surface deformation, or based on equal deformation at the interface. But this is the empirical formula we talked about before. Based on the test results for control, we can back calculate the zero modulus for the base course. And we also can calculate the one with geosynthetic. You have a reduced permanent deformation, that you will back calculate higher equivalent modulus. Based on that, we can calculate the modulus improvement factor. Okay, the equivalent modulus divided by the one without geosynthetic, you can get the improvement factor. The improvement factor can be determined from repeated triaxial tests or large plate loading tests or traffic tests. But one thing need to point out, you have to use permanent deformation rather than the zero deformation. But we did a study for cycle plate loading tests at the 3 different criteria with 3 different base course thickness and with different conditions without geosynthetic, with 1 type of geogrid, 2 second type of geogrid, and we back calculate the modulus with modulus improvement factors. So based on the interface strength, based on the surface permanent deformation, based on the permanent deformation and at the interface. What we found, the best results will be back calculated based on surface permanent deformation. So that is the conclusion based method in terms of permanent deformation are more reliable than those in terms of interface stress. But I want to move on to talk about 2 case studies very quick. So this is the one dealing with Geogrid stabilized access load. For this case, there's a high ground table. The original design with the section of 1.2 meter with very soft subgrade 2%, and use 2-layer triaxial geogrid, reduce the section to 60 centimeters to avoid the ground table. So here basically show you the picture. This is the before use the geogrid. As you can see, when you exit down, you will see the ground table. That creates a problem for construction. But if you use the geogrid, then you will not encounter the ground table. Then you can place a geogrid, place the base course to finish up the project much faster. The second case I want to share with you regarding geocell stabilized unpaved road that is in Canada. So we're dealing with organic soil, peat soil, very soft soil, but this is a very large project. And as you can see, they use a geocell. But this is expanded geocell. This is a collapsed geocell when they transport to the field. This is a close view. As you can see, they expanded geocell, they fixed at the edge. And this is at the bottom, this is a geotextile as a separate. And then you can backfill the material sand from on site. And this is basically doing the compaction, okay? And this is basically carry very heavy vehicle on top of this very soft soil with geocell stabilization. But I reached to the point to make 3 concluding remarks. 1, geosynthetic in unpaved road serve different functions, involve different mechanisms, and provide different benefits. Geosynthetic stable unpaved roads allow larger deformations are designed based on the bearing capacity theory. The benefit of geosynthetic are to increase the subgrade bearing capacity and slow down the deterioration of base courses. But geosynthetic stable unpaved roads allowing smaller deformation can be designed based on the mechanistic imperial approach, use compaction-induced stress, or increase equivalent modulus of base course. With that, I thank you very much. See whether you have any questions.
Thank you very much, Professor Jie Han. That was a fantastic presentation. We'll just have a quick case study now from Geofabrics, and then we'll just, if we've got time, we'll answer a few questions at the end, if that's okay.
Yeah.
Thank you. Okay, Abid, over to yourself there to give us your case study.
Thank you, Professor Han, for the wonderful presentation. I'll just quickly present an Australian case study. I'll share my screen. Just let me know when you can see my screen.
Yep, it's good.
Okay, thank you. So my name is Abid. I work with Geofabrics as an application engineer, and I'll just quickly take you through one of the case studies where we've used geosynthetics and achieved great outcomes. So as Geofabrics, basically, we not only supply geosynthetics, but we can also work closely with you as being a designer or consultant or whatever your role on a project is. We provide free evaluations, which is basically non-certified design assistance, and we can provide free office or site consultation or visit, and we can also provide supply schedule. And just to touch briefly on the types of geosynthetics we supply for payments or working platforms, we supply non-woven geotextiles manufactured in Australia by Geofabrics using recycled plastic. And obviously, the more commonly used geosynthetics like geogrids, woven geotextiles, geocell. And also, lastly, I'll just touch upon Megaflow, which is a flat panel drainage pipe manufactured in Australia by Geofabrics using recycled plastic. So now on to the case study. So this is about Mount Gellibrand Wind Farm in Victoria. And I'll quickly describe the project in brief. So this is located 25 kilometers east of Golak in Victoria, and it basically comprises 44 wind turbines, each generating 3 megawatt with a total capacity of 132 megawatts. And this project alone can supply clean and green energy to 90,000 houses. And the project cost was 258 million Australian dollars. And so quite heavy equipment was used on site, rotors with 125-meter diameter on 87.5-meter high steel towers with tip height of 150 meters. The main thing, looking at it from Geofabrics or perspective, is that the client needed to construct 27 kilometers of access tracks, 92,000 square meters of hard stand areas associated with 16,000 cubic meters of structural concrete for the wind turbine foundations. Now coming to the access road, the access road not only had to carry very heavy construction vehicular traffic, but as well as it had to cater to the movements of a 600-ton track crane, which is quite a heavy piece of equipment, as well as a 500-ton wheeled crane required to mobilize the turbine engines. And the subgrade conditions were quite poor, and high quality fill material was not easily available on site, and the construction had to be taken during the cold season in Victoria, so using a substandard quality fill material. And the access road thickness was arrived at using the famous Giroud-Han method in this project. For the hard stand, the analysis was carried out using the following methods: the BR470 for which is commonly used for design and working platforms, and the HW was determined using limit equilibrium methods, as well as the shear strength reduction method, basically finite element analysis, and some settlement calculations were carried out using FEA. So these pictures basically demonstrate the heavy piece of track crane in motion, so taken at different angles. And I'll just run this video and you can see. another video. So that was the track crane, and this is the wheel crane lifting the big piece of wind turbine. So the previous video was basically for the access track, where this is for the hard stand area. And so coming to the use of geosynthetics for unpaved roads, we know that it leads to cost savings and it can expedite the construction time. And obviously, we can achieve the required performance outcomes and lead to cost savings as well, and lower maintenance in the longer run. And we at GeoFabrics can provide technical support to you on your project from conception to completion. So we provide free project evaluations, as well as we can assist you with any other query. So especially for this Mount Gellibrand wind farm, GeoFabrics was there on site to help with the installation of the geosynthetics. If you've got any application related queries or evaluation related queries, you can reach out to me on these details. So I'll just stop sharing the screen from my end. Thank you.
Thank you, Bid. That was great. So we have a few questions. I think we can maybe get through maybe one question, maybe two questions quickly for you, Professor. So we've got one question here. One is that, could you advise which geogrid types have been calibrated for the Giroud-Han method?
Yeah, original calibration based on the two product, basically punch, drill, biaxial geogrid, PP geogrid, used for the calibration for the paper.
Right. Yes.
But yes. Mm-hmm.
All right. Thank you. We have another question here. So it's sort of in two parts. Number one is, what are the strain limiting values for small deformation and large deformation?
Okay. Yeah, I think that's a very good question. For most cases in the application, we measure the strength pretty small. Is like less than 1% strength for geosynthetics. Now, for the design, as I discussed in the lecture, basically there are two different applications. Mostly we based on the deformation rather than strength. Typically, for small deformation, we limit it to like 1 inch deformation. Is basically 25 millimeter. I used to with the English unit. For larger deformation, we typically talk about like 75 millimeter, 100 millimeter deformation situation for application. So I think there's also question related to the property. The important property is not the strength, as I mentioned in the presentation, really dealing with the small strength modulus like stiffness of the geosynthetics. The best thing, of course, is you perform like a performance test with the soil. Not only the geosynthetics is important, also the interaction between geosynthetic and the soil is important. As I mentioned, the actual size with aggregate size, and this is why we typically suggest you perform like a performance test rather than just index test of geosynthetics.
Cool, thank you. So, and following on from that question, there was also follow on from that. So, from the formulas presented, which of those formulas are more appropriate for the design of geocell reinforced paved and unpaved roads, and how to determine the MIF in practice?
Okay, yeah, as I mentioned, it really depends on your application. If you're dealing with a larger deformation, the one formula I mentioned carried by my former students, and that was based on a larger deformation. Okay, but that method was based on strength limit. But I also show you another case, basically dealing with small deformation, use the mechanistic empirical pavement design method. Now, regarding the modulus improvement factor, I think this is an easy way to use in the practice, and you can determine based on the cyclic plate loading test, if you can do that. Now, trafficking test, of course, you can do that as well. Now, sometimes you can use the cyclic triaxial test, but you need to be careful when you do cyclic tests. Don't use the resilient deformation. You should use the permanent deformation to back calculate the modulus improvement factor. Now, the reason why not to use the resilient deformation, if you use the resilient deformation, you will not see any benefit of geosynthetics, because the geosynthetic will not minimize the rebound, only minimize the permanent deformation, and that's good for the application.
Yeah, makes sense. All right. Well, we have a few more questions, but I think due to time, if it's okay, we'll email those questions, and you could maybe send a response back, then we can send that to the person that asked the question, if that's okay.
Yeah, sure.
Yeah. All right. Well, thank you for your time today and presenting today's webinar. I think everybody's found it really interesting, and it's given everybody something to think about. So yeah, very much appreciate it. Thank you.
Thank you for your invitation.
Yeah, our next webinar will be in February. And the details for this will be sent out in our bulletins and on our LinkedIn post. So thank you to everybody for attending. We'll see you next time, and enjoy the rest of your day.
Thank you.
Thank you.
Bye.
Bye.